GCSE Physics. This is pressure, lesson 2, and this is pressure in a fluid column. So the objectives are to explain why pressure increases with depth, and to use the equation for pressure within column height to solve problems via calculations. Okay, let's get started. So density in a fluid. So density is a measure of the compactness of a substance, and it's measured in kilograms per cubic meter. There will be a lesson uploaded soon on density, if you wish to do that one exclusively. So for any given fluid, the density is uniform or the same, and it isn't affected by shape or size. That's pretty important. So it isn't affected by shape or size, and you'll see that later when we do a question. Not all fluids have the same density, so it's material dependent. Let's move on then. Remember to pause or rewind at any point if you need to make some notes. So this is just a bit of a story. So an explorer called Vescovo he works in finance, but he's also an explorer. Solo piloted a $48 million treated submarine to the bottom of the Puerto Rico Trench. So the submarine recently at the bottom of the Atlantic, the depth was 8.4 kilometers. So why do you think it's shaped like it is? It's quite simple, really. It's to do with the pressure that's exerted. So they have to have a specific design. If it's not designed in a certain way, then the sea would, obviously all the seas above it would literally just crush it, which isn't good if you're Vescovo and you're 8.4 kilometers deep. So how deep can a human dive without scuba gear? You don't need to know this for your exam. But deep diving is defined as a dive that exceeds 18.28 meters. It's very specific. That means that most people can dive up to a maximum of that, that depth. For most swimmers, the depth of 6 meters is the most they would free dive. Free dives where you don't have any equipment. So experienced divers can safely dive to a depth of 12 meters when exploring underwater reefs. So the question is why? So when freediving, the body goes through several changes to help with acclimatization. So the heartbeat will slow by up to 25%. Experienced divers can reduce their heart rate to more than 50%. This is to cope with the pressure of the body. To cope with the pressure, the body allows vital organs to keep functioning properly by moving blood to the most important parts. It's known as peripheral vasoconstriction. Handy if you're going to study medicine. So lungs compensate from the excess pressure by expanding as necessary to allow for the changes in the body. So basically, even at that relatively short depth, there's so much pressure exerted that we get these significant changes in our physiology. Okay, let's move on. So an explanation of pressure and depth. So you need to know this for your examination. So as depth increases, the amount of mass, in this case the water above the person, will obviously increase. So this increases the weight or the force of the water acting on the swimmer from above. So that will be a full explanation of pressure and depth. This is a commonly asked question. Remember to pause if you need to make any notes. Let's move on. So there must be an equation. This is physics. There's always equations, and there is. And the pressure is equal to density multiplied by gravity or gravitational field strength multiplied by the column height. Shorthand is P equals rho GH, rho for density. It's like a P that's kind of slanted. I'll show you in a second. If you want to write the equation though and get the units, so pressure due to the column of liquid is measured in pascals, which is PA. Density of the liquid is kilograms per cubic meter. Gravitational field strength is measured in newtons per kilo or meters per second squared. And you've got to remember on Earth the value is 9.8. I'll just write that down in case you've forgotten. 9.8 meters per second squared or newtons per kilogram. And height of the column at a certain point is measured in meters. So if you're ready to move on. So we've got the equation. So pressure is rho. Now rho really looks like that. It's kind of like a P that's been knocked on its side a little bit. Rho GH. Okay, so pressure is density times gravitational field strength, which on Earth will always be 9.8 multiplied by the height. you could be asking a question to rearrange the equation. So what I'll do now is rearrange to find height, just to give you an example. So if you start with this one, we need to get height. We need to make height the subject of the formula. So these are all multiplied. So to get rid of the times density and times gravity, or times rho times g, we just need to do the opposite of timesing, which is dividing. So it would pressure divided by density times gravity would give you the height. And then for another example, let's find the density. So density, we need to get rid of a times g times h. So we do the opposite of timesing by those, and that will be dividing. So density will be equal to pressure divided by GH. Along those lines anyway. Okay. All right, let's move on. A bit more information, then we'll do some practice calculation questions. First of all though, what is this? So we've got some kind of column of water with openings at the bottom and the middle at the top. And the water is being forced out or pushed out to different distances away. So you can show that pressure is increasing with depth, and the water travels the fastest or the furthest the deeper down the column that you go. So that's typically in an examination it might give you this drawing but not give you the middle one, and then ask you to sketch it in and show where the water would go, and you'd obviously just draw in that it would be in between the top one and the bottom one. Okay, hopefully that's okay. All right, let's do some calculations. All right, let's start with these two. So if you want to pause and have a go, and then I'll take you through the answers. So first one, calculate the pressure acting at a point 20 meters deep in a column of water. The density of water is 1,000 kilograms per cubic meter. So straightforward. So pressure is equal to density times gravity times height. So we just need to put our numbers in. So density is 1,000 kilograms per cubic meter. It's always the same for water. Well, pure water. Seawater is about 1,030 actually. So G is 9.8 times the depth of 20 meters. So if we put them in our calculator, we'll get a pressure that's equal to 196,000 pascals. Or you might have written 196 kilopascals. Second one then. So we've got a pressure of 1 megapascal acting on a submarine at an unknown depth. So we're finding out depth. Calculate the depth, obviously. Okay, so we've already got the density of water from above. It's 1,000. So I'm going to write my equation. So pressure is equal to rho GH. And we need to rearrange to find the height. So that will be pressure. And then we need to divide by density and G, just like we did earlier. So density and G. Then just put the numbers in. So 1 megapascal is 1 million. So 1 with 6 zeros, or 1 times 10 to the 6 for standard form, divided by the density, which is 1,000, times 9.8. That top number is just 1 million, remember. So if you calculate that, you should get a depth of 102 meters. Okay, let's move on. So quite a few questions there. If you want to pause and have a go, and then I'll take you through the answers. So number 1, water has been poured into the container. Draw the water levels of 2, 3, and 4. So as you probably realised, for the first one, the water depths would all be identical, because the shape doesn't really matter when it's coming to the pressure of the water. The pressure of the water will be the same at all points. Alright, explain why further underwater as swimmer goes, they experience more pressure. So there's more mass, or more mass of sea or water above the swimmer as depth increases. Therefore, the force or weight of the water will have increased, which coincidentally will result in a higher pressure. And let's do the final calculation question. So a person swims from a depth of 0.6 meters to a depth of 1.8 meters below the surface of the sea. Calculate the increase in pressure on the swimmer. Now what you might have done is calculate the pressure at both of these depths and then subtracted them, which will work. And then I'll show you a different technique, but let's do that one first. So pressure is rho GH. So for each one, let's do the density, which is 1030 times G, 9.8, times the column height. So we've got 0.6 equals, we'll do that in a second. And then the other one will be the same, so rho GH. So it'll be 1030 times 9.8 times 1.8 this time. Calculate both of those. So the first one is 6,056 pascals. And the second one is 18,169 pascals. So the increase in the pressure would be the difference between them. So it'd be 18,169 subtract 6,056. Now, I might have done this a different way, but that gives us 12,113 pascals. If you did that, that will work, and it might look like that in numerous books. However, there's another way, which is quicker, and I'll show you now. Essentially, we're looking at the change in pressure. So the change in pressure is the final pressure minus the initial pressure. So change in pressure is the final pressure, let's call it PF, minus the starting pressure, the initial. So the change in pressure would be equal to, now it's rho GH, so rho G, final height, I'll call that height 2, minus the same. So what you find is that we can just factorize that. So if you're looking at a change in pressure, now mathematically it looks like this, but even if you're not quite sure on what's happened there, it's pretty straightforward. You just do the change in height and then times it by density times G. So you just do the difference in height, so 1.8 minus 0.6, which gives us a change in height of 1.2 meters. Then just apply the pressure equals rho GH. So density is 1030 times 9.8 times the change in height of 1.2. So that gives us a pressure that's equal to the first answer, which is 1211. Well, this says 2.8. So 3 pascals. So it gives you the same answer. Give or take any roundup errors. It's up to you how you do it in the exam. The second way is obviously quicker. Anyway, I hope you found that helpful, and I'll speak to you soon.